Now, of course, when we discuss about problems requiring solutions of conservations of mass, energy, and momentum simultaneously, we need a structure in problem solution. So first of all, we have to identify the problem. We have to identify what we know, what we do not know, and also we have to identify what we can include in the analysis and what we can ignore without loss of much of the generality. So we're going to learn about the structure of the problem solution. Okay. The structure of the problem is reflected on the side of the board. That we have a reactor that is no longer operating under ideal conditions. That is a non-ideal reactor with velocity gradients, temperature gradients, and concentration gradients. How are we going to relate it to conservation laws, and how are we going to solve these problems? Now, first we have to identify, of course, the bottleneck. What is your bottleneck? Then we have to identify which conservation laws do we need. And we have to identify which parameters are available and which parameters we need to estimate. All right. Once we identify those, we start solution of the problem. Now let us remember the fact that we need to set boundaries in order to solve problems, and let us plot our system potato the hypothetical arbitrary system boundary that we have set around our problem, and we have inlet and outlet streams that is flowing through this system boundary. Now, this hypothetical system potato may refer to one reactor unit, like the ones we have on the other side of the board, or may refer to multiple reactor units, or may refer to a part of the reactor unit. But here, our scale is macroscopic. Our length scale can be measured in terms of meters. Right? That's macroscopic. Then we are going to look at the interior of this system boundary, the frame that I cut, of the hypothetical frame I cut out of the system boundary is of the millimeter scale. And in that millimeter scale, we have bubbles, we have pellets, and we have combustion domains, for example. In those pellet domains, let's magnify. We're going to have, if this is our pellet, solid pellet representing the solid reactant, or solid pellet representing a catalyst. We have pores going through this pellet, connected or independent. Right? The diameter of these pores are of micrometer scale. And if we magnify those pores, let us take one pore and magnify it. Onto these pores, we have catalyst particles, which are of nanometer scale. On these catalyst particles, the nanometer scale catalyst particle in the micron scale pore has angstrom scale sites over which our reaction A going to B take place. However, A adsorbs onto the surface, becomes A star. The reaction can proceed forward and backward, and this A star converts to B. This reaction also proceeds forward and backward. And of course, we have this A to B reaction going in both directions in the microscopic scale catalyst pore. However, we have to take into consideration the fact that B can migrate back and forth in this pore, as well as A can migrate. Therefore, in this microscopic reactor, while we might have a concentration that is a C and a temperature that is T that represents the bulk, we might have a different concentration given by C prime, different temperature given by T prime, that is on the millimetric scale of the catalyst, that is averaged out, which might be different from the concentrations that we encounter within the pores. Let me call this C double prime and T double prime. And to which precision that we are going to estimate those concentrations and those temperatures is going to be the topic of this course. So in the next section, I will be discussing the length scales, time scales, and the details. I will summarize this picture as a table for your reference.